All right, so now we're going to kind of wrap up this whole unit by looking at how we name um, compounds in general chemistry. So the fancy term we give this is nomenclature. That's just naming compounds. And what we're going to do is go from formula to the name and vice versa. And you'll be responsible to do that. So if I give you the formula, you should be able to name the compound. If I give you the name, then you should be able to give me the formula of the compound. And this, like other things from this unit, is something you have to practice. It does not come naturally. And these rules that I'm going to be giving you are not just arbitrary or, something that I decided. There is a standardized naming system that the entire scientific community uses. It uses the exact same rules, the exact same procedure for naming compounds. And I want to highlight something important. Don't trust Google to do your naming for you. Because a lot of times it might come up with, especially AI, will just come up with either some randomly incorrect thing, or will give you like an old or common name that is not based off of this standardized system. So we're going to look at this in terms of the types of situations that you will come up with. So the first one, we're going to look at naming ionic compounds with fixed charges. So those are like those main group elements that have one and only one charge. Um, so we won't be looking at transition metals, at least right now. We will probably on the next page. So an example, or I'm sorry, exception to this is zinc. Zinc's a transition metal, but it's almost always +2. And silver as a transition metal, we're going to include that in here because it's always +1. And the way that we name an ionic compound in this manner is we're going to name the cation, which comes from the metal, and then name the anion, but we're going to change the ending to IDE. And again, the um, anion comes from the non-metal. So what do I mean by change the ending? So like, for example, fluorine as an ion, F minus, that's called fluoride. Or chlorine, or the ion of chlorine, we call chloride. I minus would be iodide, H minus, hydride, O2 minus, oxide, S2 minus, sulfide, and N3 minus is nitride. So let's do a couple examples. So here we have NaCl. Well, we're going to name the cation, not change it at all. So we put sodium. And then with chlorine, the end of the name changes to IDE. Now, the thing about this type of nomenclature is we don't have to indicate the number of atoms in any sort of way. Because these atoms have fixed charges, we're just relying on the reader to know, a little bit about chemistry and recognize that if you have this name, that you should be able to kind of conjure in your mind how many atoms there should be in that compound. So, for example, with CaBr2, the first name is based on the cation, so this is calcium. We don't change it at all. And I'm not going to indicate that this compound has two bromines in it. I'm just going to name the second name as bromide. I don't have to indicate the number because when somebody hears the name calcium bromide, they know, okay, well, calcium has a +2 charge. In order for this to be neutral, if bromine has a -1 charge, I got to have two of them so that the charge ends up to 0. Now, let's do a lot. We're going to do some more examples. So we're going to do this, and then we're going to start with a name and go to a formula. And then we'll do KCl, we'll do Al2O3, we'll do aluminum sulfide, and then silver oxide. So we're going to get practice doing both ways of or both directions in nomenclature. So with MgF2, we're given the formula. So just name cation and then name the anion. But we have the IDE ending. All right, now going from name to formula might sometimes be a little bit more difficult because we have to look at each ion separately. So let's look at zinc. Well, zinc is generally always +2. And nitride, that's the N3- ion. Now we could do a whole bunch of math and kind of come to the same conclusion, but we're going to do something easy here. I'm going to take the number of the cation and make it the subscript for the anion. And I'm going to do the same thing here in the other direction. And what that basically, that gives me the formula right there. ZN3, N2. And then I just make sure that it's the lowest, it's like reduced to the lowest possible numbers. And there's my formula. All right, so with KCl, I'm going to name the anion without changing it at all, potassium. And then I name the anion and change the ending to IDE. All right, Al2O3, again, name the cation, don't make any changes. I don't have to indicate that there's two aluminums there. And then oxygen as an anion is named oxide. Again, when somebody hears the name aluminum oxide, they should have the knowledge to know that, well, there's two aluminums and three oxygens in there. I don't have to indicate the number. All right, let's go the other way now. In the next example, we have aluminum sulfide. That's the name. In order to go to the formula, I need to know the individual ions involved. So aluminum is +3. Sulfide is the S2- ion. I'm going to do the same thing I did up above. I'm going to take the 3 and make it the subscript for sulfur. I'm going to take the 2 and make it the subscript for aluminum. And that gets me to my formula, Al2S3. And now with silver oxide, the silver ion is Ag+1. That's one of our transition metal exceptions. It's always +1. And then oxide is the O2-. And I could do the same thing if I wanted to use the little crisscross method, or I could just recognize, well, I need two silvers to balance out the -2 charge of the oxygen. So Ag2O. Now, how do we deal with those transition metals? So we're going to look at how we name ionic compounds with variable charges. And again, that deals with transition metals, except zinc and silver. Those only have one charge. The other transition metals could potentially have a wide number of possible charges. So the only thing that changes with this is the name of the cation slightly. We're still going to name it as it appears on the periodic table. But right after that name, we're going to put in parentheses, we're going to indicate the charge of the metal but in Roman numerals. Why they use Roman numerals, I don't know. That's what the old guys that sat in the room and said, here's how we're going to do everything. And just in case, I don't want to assume you know how to write Roman numerals or anything, but the ones you should know. So we use an I for +1, two I's for +2, three I's for +3, IV for +4, V for +5, VI for +6, and then VII for +7. And it generally doesn't go any higher than that. So that's where we'll stop with the Roman numerals. And then we name the anion just as normal. So the name of the anion with an IDE ending. All right, so let's look at a couple examples. So let's look at CRO. Chromium is a transition metal and can have a variety of different charges. In order to name this, I need to know what charge it has. So if the oxygen is -2, or actually 2 minus, I'll put it the correct way. In order for the whole compound to add up to 0, chromium has to be 2 plus. So when I name the cation, I'm going to say chromium. I don't change that at all. I'm just going to put in parentheses in Roman numerals the charge. And then I name the anion. Okay, let's look at Cr2O3. So I know again, the whole charge has to add up to 0. Oxygen's always -2, or almost always -2. There's 3 of them, so that means the whole negative side is -6. All the chromiums then have to add up to +6 to balance it out. I have 2 chromiums, so I'll divide by 2. And that means chromium here is 3 plus. So in this name, I will say chromium 3, Roman numeral 3, oxide. Now, how about going the other direction? What if you're given the name? So let's look at lead 4 chloride. The Roman numeral tells you the charge on the metal. So that means in this compound, lead is +4 and chloride is always -1. So how do I get to the final formula? Well, in order for it to add up to 0, I need 4 chlorines to balance out the +4 charge of lead. So PbCl4. Now, how do we deal with ionic compounds with polyatomic ions? It's the same process, except you don't change the ending for the polyatomic ions. You just name them as is. So, like for example, nitrite. If nitrite appears in an ionic compound, that's how you name it, nitrite. Or sulfate. Sulfate is the SO4 -2 ion. You just name it as sulfate in the ionic compound name. So let's look at this here. So KNO3. Well, K is potassium. And I know that, potassium is an alkali metal. It has a charge of +1. I don't have to indicate that because that's the only charge it will have. And nitrate is the NO3 minus 1 ion. So I just indicate the name nitrate. That's the name of the polyatomic ion. I don't change the ending at all. Okay, what if I'm given the name iron 2 sulfate? Well, you just approach it in the same way as before. The iron, or I'm sorry, the Roman numeral gives you the charge of the iron, tells you it's +2. Sulfate, hopefully you have your polyatomic ions memorized. It's SO4, 2 minus. Now I put those together now to make the formula. If iron's +2, sulfate's -2, I don't need to change how many atoms or how many ions are needed because it all adds up to 0. So I will just say FeSO4. And one little thing to add to this is how do we handle hydrates? Now we did a lab on this, and so you got a little bit of experience. You kind of saw maybe tangentially how um, they were named. But just to recap what we talked about in lab, hydrates are ionic compounds. So some ionic compounds have water in their crystalline structure. Water's not bonded to the compounds. It's just kind of like they're like caged in, so to speak. So like you can kind of see a couple examples here. Like here at the top is anhydrous copper bromide. There's no water in there. And it can just like absorb a little bit of water into its lattice. The water's not bonded to it. It's just kind of stuck in a cage there. Or the same here with CrF3. You got water molecules kind of intertwined, not bonded with the chromium or the fluoride. So the way we represent hydrates in a formula is you'll see the salt and then this big dot and then the number followed by the formula of water. The number tells you how much water is bound up into it. Now we know how to name the salt part of that. How do we name this hydrate part? Well, we're going to give that number a numerical prefix in the name. So here's some prefixes that you need to learn. A value of 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. All right, so let's name this hydrate. So I have copper, and that's a transition metal. So I need to know its charge. If sulfate's -2, copper has to be +2 so that everything adds up to 0. So I'm going to say copper 2 sulfate. And then I'm going to name the water part of this. I put a prefix penta because there's 5 waters, and then I say hydrate. Now let's go the other way. Here's the name, nickel 2 chloride hexahydrate. So let's just kind of break that down. Nickel 2, that tells you that I have a transition metal, nickel, with a +2 charge. Chloride's always -1. And the hexahydrate means I'm going to put this big dot with 6 waters. Now, what should the formula of the salt part of this be? If nickel is plus 2 and chloride is minus 1, I need two chlorines to balance out that plus 2 charge. So NiCl2 and the big dot and 6H2O.